Hello, this is Richard Collins, your instructor in ATM 101 Weather and Climate of Alaska. Today I want to discuss the solution to problem 3 of the first practice exam. Problem 3a. Which of the following has a wavelength shorter than that of blue light? The answer is 3 ultraviolet radiation. Green light has a wavelength longer than that of blue light. Red light has a wavelength longer than green light and blue light. And ultraviolet radiation is the radiation that's invisible to our eye that has a wavelength just shorter than that of blue light. Problem 3b. The Sun emits a maximum amount of radiation at wavelengths near blank, while the Earth emits a maximum amount of radiation at wavelengths near blank. The answer is 1, 0.5 micrometers and 10 micrometers. The Sun emits at 0.5 micrometers or 500 nanometers. The Earth emits at 10 micrometers or 10 microns. The reason for this is that the Sun is warmer than the Earth, and therefore, as a warmer body, it emits light or radiation at a shorter wavelength. In astronomy, this is used in looking at stars, that red stars are cooler than blue stars. And so answer 2, 10 micrometers and 0.5 micrometers is reversed. We've got it backwards, and answer 3 is completely wrong in that yes, the Sun wavelength is shorter than the Earth wavelength, but the wavelengths are completely wrong. The Sun emits in the visible at half a micrometer. 1 micrometer and 30 micrometers are in the infrared and beyond. Problem 3c. The atmospheric greenhouse effect is produced mainly by the correct answer is number 2, absorption and re-emission of infrared radiation by the atmosphere. The atmosphere absorbs radiation that is emitted from the ground. The ground is trying to cool. It's at a temperature of 300 Kelvin and it's emitting radiation at 10 micrometers. That radiation is absorbed by the atmosphere, primarily by water vapor and carbon dioxide and methane, and then re-emitted. Some of it goes out to space, but some of it goes back to the ground. So what's happening is that the atmosphere is now intercepting the radiation that would otherwise leave the Earth, sending it back to the ground, and therefore heating the Earth even more than the heating due to direct sunlight. And so this is the role of the atmosphere to create a planet which has a warmer climate than it would have otherwise. Number 1, absorption and re-emission of visible light by the atmosphere is incorrect because the atmosphere doesn't absorb significant visible light. And number 3, absorption and re-emission of infrared radiation by the ground is also incorrect. The ground primarily absorbs visible light in its heating from the Sun and then emits infrared radiation as it attempts to cool. Problem 3d. According to Wien's displacement law, the wavelength at which maximum blackbody radiation occurs, the correct answer is 2, is inversely proportional to temperature. The wavelength increases as the temperature decreases, or the wavelength decreases as the temperature increases. So as the temperature increases, we expect colors to shift from red to blue. As the temperature decreases and things cool, we expect the wavelength to increase from blue to red. Is proportional to temperature, number 1, is just wrong, and is proportional to density is completely wrong. The Wien's displacement law is an important law because it allows people to tell the temperature of stars and objects by looking at the wavelengths they emit. Problem 3e. If the amount of energy lost by the Earth to space each year was greater than that received from the Sun, the correct answer is 2. The Earth's average temperature would fall. If we go through a year where the energy from the Sun through visible light ends up being less than the energy we emit through infrared radiation, then over the course of the year we have a deficit of energy. We're on average losing energy year by year, and the temperature of the Earth would have to fall. The temperature represents the internal energy of a body, and so if its energy is going down, its temperature has to go down. This is an example of what we call radiative balance or imbalance. If the balance between the incoming and outgoing radiation is not perfect, then the temperature has to change. Number one is wrong. The Earth's temperature would rise. That would be an example of an imbalance where the energy absorbed from the sun was greater than the energy being lost to space. That's what happens during the day. The sunlight heats the Earth more than it loses energy due to infrared radiation, and we warm up during the day. Number two is an example of what happens at night. We have no sunlight and we just emit radiation to space, and so we cool during the night. The last choice, 3, the Earth's temperature would stay the same. That can only happen if we have a perfect balance between the incoming radiation and the incoming energy and the outgoing radiation and the outgoing energy. If they're in perfect balance, so that on average we neither gain nor lose energy over the course of a year, then the temperature should stay the same. This is the question at the core of greenhouse gases, in that we now believe that we have a small imbalance in the atmosphere where we're holding on to more radiation energy than we emit back to space, and therefore the temperature of the Earth is beginning to increase. Problem 3F. In this problem, it's a good idea probably to turn over to the diagram where you listen to my narration of the solution. Figure 3 shows how solar energy interacts with the Earth and atmosphere and how energy is transferred in the Earth-atmosphere system. The figure represents the average of the Earth for a whole year, and it's a figure adapted from your textbook. You might want to look at the original figure as you think through the problem and you prepare for the exam. Part 1. If the ground changed to a completely black surface and everything else stayed the same, how many units of solar radiation would be absorbed at the ground in Figure 3? Well, looking at Figure 3, we see that there are two places where light hits the ground. Light is incident at the ground in pathway C, 49 units, and pathway D, 8 units. The light in pathway D, though, represents the light then that is reflected from the ground, of 8 units. So at the ground, there are 57 units of light incident at the ground, 49 units are absorbed, and 8 units are reflected. If we moved to a completely black surface, all the light incident at the ground would be absorbed, none of it would be reflected, and so we would have 49 plus 8, or 57 units completely absorbed at the ground. When we talk about the Earth's surface, we say that the Earth's surface has an albedo of about 14% averaged over the whole globe. The 14% is essentially the fraction 8 over 57, the percentage of the incident light that is reflected, expressed as a percentage, 8 over 57 multiplied by 100, giving us our 14%. Part 2. In a cloud-free desert region, how many units of solar radiation will be absorbed at the ground in Figure 3? Well, if we look at Figure 3, we see that if we remove clouds, we remove pathways A and E. The absorption by clouds, 3 units of radiation in A, the reflection by clouds, 16 units of radiation in E. If that radiation now comes to the ground, we have 19 extra units of radiation coming to the ground. Of that, 14% will be reflected, and 86%, or 49 over 57, will be absorbed. So we've now added extra radiation, the 49 units that were originally absorbed at the ground, and now the fraction of extra radiation that's incident on the ground, the fraction of the 19 extra units. So 49 over 57 multiplied by 19 added to the 49 gives us a total of 65 units of radiation now absorbed at the ground. Part 3. What is the value in units of the total energy input to the Earth-atmosphere system in Figure 3? The input radiation is the radiation coming from the sun that is absorbed in the atmosphere. We see at the top of the atmosphere there's 100 units of sunlight coming in, but through pathways D, E, and F there is a total of 31 units being reflected to space from the atmosphere, from clouds, and from the ground. And so we're left with that there's 69 units of radiation being absorbed in the Earth atmosphere system. Part 4. Which two processes represent the greenhouse effect in Figure 3? The answer is J and I. J represents the absorption of infrared radiation that is emitted from the Earth. The Earth is emitting radiation through pathway G. Some of that radiation goes in pathway J into the atmosphere. Some of it goes in pathway H back out to space. The absorption of radiation through pathway J heats the atmosphere. The atmosphere now re-emits that radiation. Some of it comes back to the ground through pathway I. Some of it goes out to space through pathway K. It's that extra radiation coming back to the ground through pathway I that gives us the greenhouse effect and the supplemental heating of the Earth. Part 5. Think about late November in the region of Alaska where you live. Looking at Figure 3, can you identify two important processes that change their energy compared to these global values? In late November in Alaska, the sun is low on the horizon, and so the incident radiation from the sun is very weak because at a low solar angle, the sunlight is spread out broadly on the ground, and therefore the intensity of the heating is much reduced. So the first thing that happens is that C is much reduced. The second thing is that most of Alaska we can think of as frozen. And so we don't have evaporation of water and latent heat release. And so pathway M is much reduced because we don't have transfer of energy through warming of water, absorption of heat by the water evaporating and then condensing in the sky and releasing its heat through latent heat of condensation into the atmosphere. So pathways C and M change significantly in late November, and as I said, C decreases and M decreases. So we have less radiation coming in. We also have less energy loss through latent heat in M, but the loss in C far outweighs the energy the ground gains, if you will, by M being reduced, and so overall the energy at the ground goes down in late November, and as you know, each November day just gets colder and colder in Alaska. Part 6. Using the ideas in 5, can you argue whether the temperature of the ground should get colder, warmer, or stay the same with the passing of each late November day? And this is a problem that we've already talked about in Part 5. It also relates back to the multiple choice questions about energy balance. If we reduce C significantly and we reduce M a little bit, we're now having on average less energy being absorbed by the ground. The amount of energy being lost to space hasn't changed significantly, and so on average the ground gets colder and colder each day because it's losing energy on balance each day. So as solar altitude decreases with each day in November, there is less solar energy absorbed at the surface. Meanwhile, the surface continues to radiate infrared radiation to the atmosphere, and on balance the ground loses more energy than it gains, and there is a deficit of energy and the ground cools day by day. Before I continue with problem 3G and 3H, I just want to discuss figure 3 in terms of the figure that you may have in your textbook. Different editions of the textbook have slightly different versions of this figure, and it's important for you to focus on the big picture and not get caught up in the details. One of the main differences that I see in figure 3 in this exam and some versions of the textbook is that in some versions of the textbook, pathway F and E are combined together into a single pathway. So the 7 plus 16 units in F and E are combined into 23 units, and pathway A and B are combined into a single pathway of about 20 units. So it doesn't affect how we're working through the problem or your core understanding. Pathway A and B represent the visible light that is absorbed into the atmosphere and into clouds. Some pictures like to combine that into atmosphere and clouds together. Pathway F and E are the light reflected from the atmosphere. Remember, the atmosphere can reflect light, just the air itself. The blue sky tells you that atmospheric molecules interact with sunlight. They're not transparent completely, and so the reflected light from the atmosphere molecules themselves and the clouds can be combined together as the total reflection from the atmosphere. So that's the major difference in the pathways that we see in different figures. It's just they're combined differently. But the big picture concepts remain the same. The visible light coming to the ground, the visible light absorbed in the atmosphere and clouds, and the visible light reflected from the ground and reflected from the atmosphere and clouds together. The precise numbers at this point shouldn't concern you. What I'm really interested in is the big picture numbers and the relative values of the numbers, that the dominant pathways are pathways C, G, J, and I, and K are the big number pathways, if you will, where we've got numbers over 40. And as we talk about the general balance, those are the big numbers in terms of how the greenhouse effect works and how solar radiation is absorbed by the atmosphere. Don't worry about these numbers in terms of tweaking them down to the final decimal points. I will say to those of you that if you look at any research material, this difference that you're seeing between different textbooks is an issue when you get to core atmospheric science research, because the greenhouse effect is about an imbalance in these pathways on the order of about 1 unit. What we're trying to find definitively is the value of I plus or minus 1 unit, and the current greenhouse effect, where we think we have global warming due to increases in carbon dioxide, water vapor, and methane, is about the fact that I has increased by about 1 unit relative to other processes, and therefore we are getting supplemental heating of the planet that is global warming. As I say, the most important thing is to understand the major pathways and the relative values of the numbers. In active research, we are tweaking these values plus or minus 1 unit, but we're not changing them by 5s and 10s of units. Problem 3G. Explain the roles of conduction, convection, and radiation and how the sun heats the air in the troposphere on a sunny summer afternoon. Conduction, convection, and radiation are the 3 methods in which energy is transferred. Conduction is transfer of energy within a material, where as we heat the material, the atoms and molecules in the material vibrate more strongly as their energy increases, and they vibrate against each other and they transfer heat through vibration, and the energy travels through the material based on contact between the atoms and molecules and transfer of energy through vibration. Convection is the way that heat is transferred in fluids. If you think of a pot of water on the stovetop with grains of rice in it, you know that the grains of rice rise in the water and fall in the water, and we have what we call convection cells, and this is because the water in contact with the bottom of the pot is heated more than the other water through conduction. It gets warm, it expands, it becomes less dense than the water around it, and therefore it becomes buoyant and rises. As it rises, it cools at the top of the pot, becomes denser than the water around it, and falls again to the bottom of the pot, and so we get a stable convection cell that we can see the grains of rice riding the convection cell in the pot. Finally, radiation is the method by which energy is transferred in free space without any mechanical support from atoms and molecules. This is how radiation travels as electromagnetic waves. Energy travels as electromagnetic waves as radiation. And this is a great problem in physics of the early 20th century, the idea that energy can travel without support in a vacuum as electromagnetic waves. So on a sunny day, the sunlight travels from the sun to the earth along pathway C in figure 3 as electromagnetic waves. They are incident on the ground. Their energy is absorbed and heats the ground. The ground is now warm. The air just above it that's in contact with the ground is then heated by conduction. That air becomes less dense than the air around it, and it becomes buoyant and rises, and so we now have a convection cell, and it's the convection that carries the heat up into the troposphere. And that's what we're seeing when we see pop-up little cumulus clouds on a summer's day. The small clouds are being formed in the rising cell of those convection cells, and so they become a visible marker of the convection cells that are being formed by the heating of the ground. Problem 3H. Current climate models expect the Arctic Ocean to become ice-free in summer by the mid-21st century. Explain how this might change the energy balance and the surface temperature in the Arctic in terms of albedo. Is there any process that might reduce this change? Please explain how it would do this. So, as sea ice melts, we move from a high albedo surface, a high shiny surface that reflects a lot of light, to a low albedo surface, the open ocean, which is dark. And so increasingly, as we go from ice to water, C is increasing and D is decreasing. The energy that would have been reflected in D is now being absorbed in C. And so the Earth's surface should get warmer. The ocean should get warmer. This becomes a runaway effect because as the ocean gets warmer in the summer, it freezes later in the winter. And so it can absorb heat longer through the summer and carry some of that heat through the winter. And this is one of the scenarios for how the Arctic ice pack may actually be significantly diminished over time. However, if the water is open to the air for a longer season and is warmer, there is perhaps going to be more evaporation from the water into the air and more possibility of cloud cover. If there's more cloud cover, then A and E will increase, particularly E, that the clouds will reflect light to space, so this will counteract the increase in C due to the ice becoming water in the ocean. And so the warming due to the decrease in ice cover would be offset by cooling due to increase in cloud cover. So that is the uncertainty in our current scenario of how the Arctic Ocean will behave. The role of clouds and how they will adapt in climate change is one of the significant and major uncertainties in climate change models. We have no doubt about how greenhouse warming works, but the great question is if the amount of cloud cover on the planet changes significantly in a greenhouse changed climate, then perhaps the effects of E will counteract the effects of an increase in I. However, regardless of what happens, that is going to be a significantly different climate system. The average temperature may remain the same, but a cloudier planet with more greenhouse effects may be a very different planet from the planet we currently enjoy, even though the average temperature may stay the same.